My name is David Markus, and as it says, I'm a machine learning evangelist. 23 years of always trying to find ways to inject machine learning workflows into everything I do, professionally and academically. And so I hope you can follow along with me, and I'll try to show that it is indeed easy to get working with Python and machine learning inside the OpenDetect environment. If I make it look difficult, then I've failed hideously today, so I appreciate your patience. So we'll just do a little bit of an outline. We'll talk about the OpenDetect machine learning plugin just a little bit for people who are unfamiliar with it. We'll talk about the development environment, again, for the people who are unfamiliar with some of the parts of it. And then we'll put it all together inside of a live demo. So moving quickly, OpenDetect is a free seismic interpretation system. It's simultaneously also a free software development platform. It's open source. You can download it on GitHub. And of course, you can develop in C++ and now in the Python machine learning environment. You can develop your own plugins or commercially share them. And of course, it's extendable with closed source commercial plugins. And those may be plugins that your organization also develops internally and doesn't share with the outside world. And there are multiple vendors who create commercial plugins for OpenDetect. And of course, all of these are supported by DGB Earth Sciences, the host of this webinar. So we use machine learning to find and delineate complex relationships and structures in geoscience data sets. So clustering, classification, regression are common examples. If we're looking at seismic only, we could be talking about clustering seismic for facies identification, imaging faults, transforming seismic to broadband, etc. In wells only, we could be predicting missing logs, classifying lithology, and if we're putting seismic and wells together, we might be trying to predict rock properties. So the machine learning plugin comes with pre-trained models. For example, there's a UNet model for identifying faults. It has a robust pre-trained model that identifies the faults based on fault and fracture attributes generated from within OpenDetect. And we'll look at that in some detail in the demonstration. And our pre-trained models may also be developed and shared within an organization. So as a commercial machine learning plugin, it links OpenDetect to Python, TensorFlow, Keras, Scikit-Learn, and of course other user selectable modules. It really speeds up machine learning research and development in that data I/O is transparent to the developer. It has access to all the workflows in OpenDetect. It's an integrated plugin which allows training and application of models directly within OpenDetect. The external Python development environment allows model creating, training, and experimentation in a programmatic setting. The full ecosystem of Python open source modules are available to augment development. And most importantly, you can create repeatable science with Python notebooks. And I say that as most importantly because the mantra of repeatable results, repeatable science, sharing models is really the way we should all be working. And of course, that leads me to the last point, is that we can share and deploy those models within an organization and or publicly. So machine learning in two bubbles is basically this, right? So we have some answers and we have some data, and the machine does something. Some magic occurs in that bubble, and some rules come out. And then we can apply those rules as a model to other data, and we can make predictions. So that is, I think, the simplest way to describe machine learning. I borrowed this slide from a Google I/O talk. I added the extra arrow in the middle because I think it tells a better story with that added. So again, borrowing a slide from them. A training workflow is really this data ingestion and transformation. And so we'd like to do most of that inside of OpenDetect. So you would load well logs, load seismic data, do some conditioning of those things inside of OpenDetect. And then you would want to do the model building using either the internal machine learning toolkit or our own custom environment, which we're going to use. And of course, you can use pre-made estimators like they have inside of OpenDetect with the UNet pre-trained, pre-made estimator. And so in that case, you don't have to do a lot of training. In fact, you don't have to do any training with the pre-saved one. But if we are doing training inside of OpenDetect, modifying parameters, we would like to be able to monitor what's happening. And so we use Tensorboard. And we'll look at that in a few slides and then live later. And of course, saving the model and sharing the model. I would have added saved model and shared model is really the important point of this slide. So inside of the development environment, inside of OpenDetect, it has quite a sophisticated architecture. And so aside from OpenDetect, there's OpenDetect as a viewer. There's what they call the Bokeh viewer. I don't know if I pronounced that correctly or not. That's basically a link to be able to allow you to use a lot of the machine learning TensorFlow tools inside Python run tools inside of OpenDetect's native windows. There's the machine learning plugin, which has its own workflows, pre-trained models. That's linked to Python. Tensorboard rides on top of that and allows us to monitor our training sessions. And of course, through the development environment, we have integrated development environments like Spyder, Visual Studio Code, and we can use those to do very low-level things in TensorFlow or high-level things in Keras, which leads us into Keras and TensorFlow. So Keras is a high-level API written in Python, provides a human-readable interface to TensorFlow. It's easy to implement machine learning algorithms without knowing the implementation details, and you can select distributed or multi-GPU processing, again, at a high level. TensorFlow, on the other hand, is a very low-level API. It's written largely in C and C++. It has native GPU code in it, and it has API implementations for Python, C, Java, Go, etc. And it provides engineers with performance tweaks by working with low-level functions. So the example at the bottom is actually Keras, and it shows how easy it is to create a sequential model. And so we just add several layers and their shape and what other kinds of parameters, and we're off to the races with minimal amounts of code. So in OpenDetect, building a model, of course, is reading and pre-processing the data. We use the OpenDetect API to access that pre-processed data that comes from inside of OpenDetect. And so this is actually a circle. And then we can use Keras, choose a distribution strategy, whether it is on the CPU or the GPU. We create our saved model and we can deploy it back to OpenDetect. We can test and then we can repeat the process over and over again. So as we're training, we want to monitor how things go. Training can take a long time. And so we use Tensorboard to understand things about statistics about our accuracy and other kinds of performance metrics so that we can compare between runs, and then we can also adjust our parameters and see if we're doing better or worse than we were before. Some models may never converge, so we want to know that also. If the model's not improving, we should stop what we're doing and start again. So the OpenDetect API is in several portions. It's a growing animal, so to speak. We're constantly adding to it, and we will add to it more as the developer group grows and more people use it and make requests for functionality. I'm probably one of the bigger drivers of new functionality at the moment. But after this webinar, I hope indeed it will be the people on the other end who are watching me who are requesting additions to this environment, to this API. So the Python API is really an ecosystem of Python applications. And so it provides an interface between OpenDetect and the HDF5 format. That's a format we use. It's a high performance format for storing data. And of course, we have the Bokeh server for inter-process services, as I described, and the Keras extensions with OpenDetect specific enhancements. So the basic idea is that it allows retrieval of data and models from OpenDetect and putting them back in. So database reads and writes, model extractions from the machine learning plugin, model creation, training, and application in a development environment, and model injection back to the machine learning plugin. And of course, we want to take advantage of hardware where models are difficult to train, easy to apply. We want to do the training perhaps on the strongest workstation we have in the office, and then deploy the models onto weaker workstations because the application of the model often doesn't require anywhere near the horsepower that the training of the model did. So we have two basic sets of tools, Python tools, like kind of generic tools that allow us to use communicating with OpenDetect's database and things like that, things that aren't really machine learning specific, but allow us to work with OpenDetect inside of Python. And then we have what we call the DGBPy package, which are ML specific tools, machine learning specific tools, and they give us direct access to models and data. We can do model building, training, and in applications external to OpenDetect, bring those things back into OpenDetect. And because we can directly access the data in the OpenDetect database, we can begin training and applying the model platform independently outside of OpenDetect. So we will move on to the live demo. So the IDE in the notebooks we will discuss inside the live demo. So please wait for me to change from PowerPoint to OpenDetect, and I'll be right back. OpenDetect version 6.6.2. This is the version that is currently shipping from the website. It's used by clients. It's also in the free version. We are using the F3 demo dataset, also available from the OpenDetect website. The magic about this dataset is that we can use it with the machine learning plugin for free. Normally, the machine learning plugin is something you would buy for use on your own data, because it's a very valuable tool. So let's start by configuring the Python environment. So we do that by going to Utilities, Installation, and Python Settings. So what we can see right away is that it has a Python environment set up by default, and that is automatically selecting CPU or GPU based on your hardware configuration. You can choose a system configuration that you've set up yourself. This is dangerous because it requires a lot of effort to do correctly. You're better off to just use what comes out of the box. But if you wanted to make your own clone of one of the internal virtual environments, you could do so by using a custom environment. And so what you could do is you could go to where OpenDetect is set up. And so we'll go there. And in the Python directory, we have these two environments, the CPU one and the CUDA one. Now, we could clone these. The best way to do so is using the virtual environment clone tool in Python. And then you could preserve the original ones as they were installed. And you could then modify to your heart's content your own. And if you broke it, you wouldn't have to install all of OpenDetect again. You could just reinstall these. So we'll select this as a directory, and you can see that now we can choose one of those virtual environments that are inside that directory. So we'll just continue on with the internal environment. And we've set up our custom module path already, but we can do that here. We can add other paths to this list. And this is where our custom code will be found by the OpenDetect API and our IDE when we are doing our editing. So we can use a different kind of IDE. Normally I use Jupyter Notebook. Spyder comes shipped out of the box with OpenDetect. So I will select that for now. We can test the installation by clicking on Test. And we can see that the TensorFlow and other modules are properly installed and working. And we can launch a prompt to verify everything is working as expected. So let me select OK here. And let's ask Spyder to start up while we go over here. And we're not currently working in the directory we'd like to be working in. So let's go to our machine learning work. Webinar. There we go. And we can use a live terminal, Python terminal, to check to see if everything has been set up correctly by importing DGBPy. And having no error return, we know that the environment is set up correctly. We can exit from here. Now, normally, Jupyter Notebook is not installed by default in this version of OpenDetect. So what we would do is we would just do a conda install notebook. And because we use mini conda, it's often better to use the conda rather than Python's pip when installing packages. Sometimes the packages won't be found by conda, and you can do it by pip, or you can install it yourself from source or anything like that. But it's best to try conda install first. So when we press enter, we'll see that, of course, Notebook is already installed. It'll just verify that it is. So while it's doing that, we can go and look at the Spyder IDE. And this is really a nice full-service IDE. You can do step-by-step debugging. It has an interactive terminal. And we can get started by opening up one of the example files. And we can also verify that everything is working correctly by doing them line by line in the interactive shell. And we'll just pick the first one. So now we're going to point to a HDF5 file. It's specified by the H5 and extension. Then we can get some information about that. And when we print it out, pick sets infos, we get back a JSON object that has all kinds of information about this data file. And that is, this is a seismic classification, what the input shapes are, the output shape, various identifiers for the database, and other kinds of important information about this particular data file. So as we write our own code, we can very quickly get the information we need to start building on top. So as I said, I prefer Jupyter Notebook for some things, but I like Visual Studio Code. So if we start code from within the Python environment, then Visual Studio Code will start up in exactly the form that allows us to work in the OpenDetect development environment without any setup. Now, the one thing you do want to watch out for is if you have recently changed between virtual environments, you want to make sure that down here you are still selecting the correct Python interpreter. So we don't want to be choosing the CPU one. We want, in this case, the GPU one. And the current one is the GPU one, so everything is okay for now. And if you are using the built-in Jupyter Notebook inside of Visual Studio Code, you may want to verify when Python starts that it is also set to the correct interpreter, because sometimes they will point to different places based on what the notebook was open in last time. And so we can trust the notebook and then we can move on. But we're going to work with Jupyter Notebook from the traditional Jupyter Notebook server. So I'll close code for now. And so we start that by typing Jupyter Notebook. Okay. Notebooks are great because basically it's reproducible science at its best. So if we go and create a new workbook in Python, it just starts out as a blank canvas. And it's a canvas of cells, and each of those cells basically can take 3 different configurations. And that is code, markdown, which is essentially HTML, and raw text or something else that will pass through unmodified. And so if we look at one that's already been populated, we're going to use for the demonstration, we can see it has nice formatting. We can insert images, links to websites. We can put live code. And so let's clear this one first. Let's clear the output from before. So now we start with a blank notebook. And so in this demonstration, we're going to show you how we can access data that's been extracted in OpenDetect and then train a model on it, our own custom model, and then put that back into OpenDetect. And so why don't we switch to OpenDetect for a moment and see how that works from the machine learning plugin side. Start up machine learning, and we can see we can work with wells, say for lithology prediction, seismic in wells for, say, rock property prediction. But we're going to concentrate on seismic image segmentation today. And the UNet 3D fault predictor is a pre-trained model inside of OpenDetect, very robust, as we said before, that is image segmentation. So we're going to create our own and train it outside of OpenDetect and bring the data back inside OpenDetect. So we click Go. And there are other webinars that cover the details of the machine learning precisely, but here's where we really want to select our data and then be able to use it outside of OpenDetect and bring it back in. And so we'll go and we say, okay, this has the fault likelihood volume that we want. It's the project that we want, but we'll select a small sub area. For the purpose of the webinar, we choose a very small one so that things can behave basically interactively. We click OK, OK, and then we choose that volume that we want. And the volume I mentioned is this fault likelihood thin from dip steer median filtered seismic. And what that looks like is over here. This data was created using the faults and fractures tool, which we find under processing faults and fractures, and it uses a lot of computational effort. A volume this size can take several days, depending on the hardware, to come up with this volume, but it's already been done, and we're going to use it as a training data set, a label data set for our seismic, so that when we train the neural network, the UNet, to look at the seismic, it has these labels, and in the future, the trained UNet will not need this, and it will be able to very rapidly use what it's learned to try to identify these from within the seismic, and it should be much, much faster than this took. And so that's the advantage, that even neural networks take a very long time to train. They can take an extremely long time to train and parameterize the right way, but once they're done, their operation is super fast. It can be nearly real time depending on the size of the GPU card that you have. So let us go back here and say, yes, this is confirm the volume that we want, and we click OK. We're going to choose an output, and in this case, I'll call it Webinar Training 2. Webinar Training 1's identical, but just for the point of showing how it works. So yes, it exists, and off we go. It takes about 10 seconds, 15 seconds for something with 194 positions. The whole volume could take several hours to several days, depending on the size of the volume, to do the training extraction. And of course, the more training data you have, the better off that you're going to be for tuning your model to see things in lots of different situations. And so if we go now through the traditional training, we would do it here. So this starts off up what's called a Bokeh canvas. And this is a link to Python and Keras and TensorFlow. And we can select training parameters, we can select the output model, and we can do all of that here. And if we click run, it would open up the Tensorboard. We could look at the progress there, but that's the normal machine learning plugin. So we're more interested now how we can work together and do this step outside and then apply that back inside of OpenDetect. So the full circle, as I showed in the PowerPoint. So if we go back to our Jupyter spreadsheet, here it says Jupyter spreadsheet, Jupyter notebook, we can start running down cell by cell. So of course, markdown cells will do markdown. This will import everything we need, including our repo. When it's done, it should tell us that TensorFlow is ready for action, and it is. Is the GPU available? Yes, it is. We can get information about the GPU, the batch sizes that are available. And then, of course, we can load our data. And in the next few cells, we can query the object to get its properties. So again, it comes back as this JSON. And so we can see that there's a seismic image transformation, what the input shape is, the output shape, and all those things. And we prepare the information that we need to create the model. In that case, we wanted the input shape and the number of attributes. And then we get on to training. And this is really as easy as it gets. We just use these parameters. So we get the defaults, and then we change the ones we want. And then we just supply the model, the training data, and the parameters. And we're off to the races. And because this is a very small data set, it will take just a few seconds for each epoch. And depending on these parameters and other parameters we can set, it can take longer or more epochs or less epochs. This one finished before it reached number 15. So typically if they go to 15, it probably means you either don't have enough epochs or your other parameters need some tweaking. And this parameter tweaking is an art in itself, and we're not going to discuss that, but this is the network that it's created and how many parameters there were. And now the best part is we want to send it back to OpenDetect, our train model. So we click run here. And okay, the model is saved back in OpenDetect. So if we go back to our plugin and we go to the apply stage and we do a refresh, our training model 1i, the interactive one, is here. And so what we can do is we can proceed with that one. Data that we're going to apply it to. So in this case, it'll be the dip-steered, median-filtered data, the seismic data. That's the data that we see over here. We're going to choose a small subset. We'll just use the same size as the training subset so that it'll be basically interactive speed when we click apply. The slightly larger subset takes about 5 minutes to process, which is too long for this webinar. So we click OK. We'll call this fault likelihood live. And then we click run. Yes, we know that it exists. Click run, and it will magically be applied very quickly once it warms up and gets everything into the GPU. Then now it's applying the learning network to the input data. It's finished. Close this. We can close this. And we can go and look what we created. We're adding it into the volume. So we can add and select data. In this case, we called it fault likelihood live. Click OK. Just warning us that we don't have a color bar yet associated with this volume. That's OK. And so let's move it into the view. 399. Maybe step it forward a bit. Turn off these other things. There we go. And so we can look to see how well that little section has trained. And if we turn it off and on, we can see that it did actually a very, very poor job with such a small training data set. So outside of this, I already ran some other runs with slightly larger, 30 times larger samples, and so we can look at what those would look like if we had more time and more time to experiment. And so let's look at this one, W2. So this one you can see is very noisy. Again, it's probably not trained enough. The training parameters aren't optimal, but we can start to see that it has the beginnings of what we would hope would be a nicely trained model. And as we move upwards in quality, we can see that once it's fully trained, we can have great confidence that what it is, it's actually showing us something similar, to the labels. But what intrigues me is that it will also find faults where there are no labels, and they seem to connect very nicely with places that in our label data even didn't get found. So here's an example right here where we have two lines crossing. Perhaps here have something. So the great thing about these kinds of models is that they can extrapolate from their own training experience. And when presented with cases that they weren't presented in the training data, they can still come up with answers that lead us to believe that they're doing the right thing. So the purpose of this webinar has been mainly to show how easy it is to get started using OpenDetect, the Python environment. And I hope that by seeing how you can use Jupyter notebooks, how you can use the IDE, Spyder IDE, and the things inside, I hope that you can see that with your own favorite tools, with the development tools that OpenDetect has created in terms of the OpenDetect API, that it's really easy to get data into your environment out of OpenDetect and back into OpenDetect. So I will conclude with that. I appreciate your patience, and with demos like this, sometimes they don't always work as perfectly as you can, but we try our best. So I thank you for your patience, and I think we'll open it up to questions now.